Okay, good morning. We are going to wrap up this worksheet, and then I have an activity for you guys to do, and then we're going to do another worksheet. And today is really focused on mechanisms and arrow pushing. Fun fact, I worked all through high school and college as a mechanic. My dad owned a mechanic shop in our small town. It was also the last full-service gas station in Wisconsin. So as a kid, I went out and pumped gas for all these people coming through. I pumped gas for like little old ladies that had lived on a farm their entire lives and had never once filled up their car with gas. They would come in because they'd never filled up their car, so they would come to us.
I have never been to a self-service gas station because I grew up here and I'm young, and one time we drove through Oregon and I didn't know they did that.
Right.
And I pulled up to the gas station and this guy approached me and I literally rolled up my windows and locked the door.
Yeah.
I just like stared at my window and he was knocking and I was like, oh my God, I'm gonna get murdered. And my husband was like, oh, he's trying to fill up the gas. I was like, oh, I'm so sorry.
It's such a strange thing. There's states where it's illegal to pump your own gas. Yeah, there was a guy that grew up in the same town as me and then moved to Oregon and then moved back. And he said coming back, he was so unaccustomed to having to pump his own gas. So then he was excited to come back to our shop because then he could have his gas pumped again. To be honest, I think I knew working as a mechanic that like the word mechanic means the one who knows how things work or makes things work. Because that's what mechanics are. They're the working of things. So mechanics are the ones that fix the things that are supposed to be working. But it never really felt like that because my job was to change oil. That doesn't really feel like the way that things work. I wasn't thinking deeply about the mechanics of the engine and the oil that was inside of it. I just had to take out the plug and let the oil drain and fill it back up. I changed tires. I didn't have to think about the way that they wore, or, I mean, I guess I did a little bit, but I didn't feel like working as a mechanic, I had to think that deeply about the mechanisms of the car. But you guys are the mechanics of chemistry in this class. That's your role. And I do want you to think about the mechanisms of how things work. So we introduced arrow pushing early on. You saw it on your midterm, and you saw it in ways that you maybe didn't quite know how to solve because we're still at the front end of arrow pushing and using arrows to explain the mechanics of how a reaction occurs. But it's going to be a major focus of ours going forward the rest of the semester. So I want to make sure that you can work out the kinks, ask the questions that are troubling you. Figure out how to ask the questions. Figure out what the questions are so that you can ask them. So today we're going to do a lot of problems on just that. We're going to work on arrow pushing and mechanisms so that you guys can try and master it. So we looked yesterday at a one-step mechanism. We said that hydroxide interacted with this methyl chloride. The nucleophile, the nucleus-loving reagent, is hydroxide. Think of that as your negative magnet. Attracted to the carbon of methyl chloride because that has a partial positive, which allows chloride to be kicked off. If hydroxide is my nucleus, my Lewis base, then the carbon is my electrophile. In fact, we'd say the entire organic substrate is the electrophile. But truly, it's the carbon that is electrophilic. I also want you to approach these and think about spotting the difference. What bonds formed, what bonds broke, how many steps do those need to take place over, and which ones can feasibly be done in what order. We worked with that when we had the reaction diagram yesterday, and we were trying to fill into different places where which structures made sense at what times. Now let's look at a two-step reaction, a two-step mechanism. The reaction that's given to us starts with an alkene. We're shown two different reactive intermediates. And then we're shown just one product. The other title that you see on this reaction is regioselectivity. Does that term make sense? Can we dissect it? Select the regions. Selectively regional? I think selecting regions makes it sound like I can choose. What if I want to choose everything? Where things are favored. So the selection of regio options, specifically, which regio option is favored? Starting material, again, was what functional group? Alkene. And the product is what functional group? No. Close. Alkyl halide. Important. That alkyl halide is important.
Isn't it a cycloalkyl halide? Is that a thing? Does it matter?
Doesn't really matter. Yeah, it is a cyclic structure, so a cyclic alkyl halide would, I guess, be okay. You could say a cyclic alkene as well. Cycloalkene. What type of reaction are we seeing? Is this addition, elimination, substitution? Addition. Consumes a pi bond. I had a pi bond and I added two things across it. What did I add across my pi bond to get to the final product? I did not add a carbon. Nope, all of the carbons that were there are still here. H and a Br. Is that what you said, Patrick?
Well, yes, it's going to see bromine and hydrogen as well.
Good. So this molecule of HBr that we're shown in the reactants is split up and added across. And we're shown that it's not adding the two groups in one step. Which is added first? The hydrogen. And then the bromine adds. So we can actually apply a regio term here. Zaitsev and anti-Zaitsev are regio terms, but those described elimination reactions. This could be described using Markovnikov or anti-Markovnikov. I'd like you guys to try and decide, is this addition reaction a Markovnikov addition or an anti-Markovnikov addition? Do you need one of those?
Is this from last class?
Yeah,
Oh, sorry, that was for me.
that's okay. Do you need one of these? Okay, you're welcome. Evelyn, do you need one of these?
No, I don't.
Okay. Oh, Saray, you do. Thank you. What do you think, Markovnikov or anti-Markovnikov? Markovnikov? Because the H, we're adding an H, so Markovnikov's rule applies. And the H is adding to the least substituted carbon. The H is added to the carbon with more H. Here's the hydrogen that we're adding.
Could you define least substituted one more time?
Well, let's define substitution. How many bonds to carbon does a carbon have? That's substitution. So,
Bonds to carbon gets carbon.
so a less substituted carbon
Got the least bonds to carbon.
has less bonds to carbon. A more substituted carbon has more bonds to carbon. So we can see that the carbon on the bottom of the alkene is bonded to less carbons, has a hydrogen, and that's where the hydrogen ends up. So this is a regioselective reaction described as a Markovnikov addition. But when we do this first step, we have to consider two different regio outcomes. Okay, another thing to consider in a mechanism, charge can never be created or destroyed. What is the net charge of the starting materials? Neutral. So what must be the net charge of the intermediate?
Neutral.
It must be neutral. But right now it appears that the two possible intermediates are positively charged, so I must be missing
The Br is negative.
a negatively charged Br. Because I've seen that the hydrogen has added. The idea is that there's a possibility of adding this hydrogen to the less substituted carbon or adding this hydrogen to the more substituted carbon. Those are the two options. But either way, hydrogen adds and a Br minus is formed. Let's draw arrows on our starting material to show the formation of the intermediates. Do you guys know what the name of this reagent is, by the way? Hydrobromic acid. If that's an acid, there must be a base. What's the base? The alkene is the base, yeah. The pi electron specifically of the alkene. If that's an acid, there must be a base. And we're seeing that the alkene takes a hydrogen, so the alkene is the base. The alkene is protonated, and the HBr bond breaks. Okay, let me see if I made a mistake. Did I give you the HBr bond? I did. It's not uncommon to write HBr as just HBr no bond. But in this step, I have to break that bond. And if I have to break it, I need to show it so that I can show it breaking. There's no way to do this without the line between HBr shown. Okay. Do my arrows indicate which carbon of the alkene uses the electrons to bond to hydrogen, and which carbon of the alkene loses the electrons entirely? They don't, and they can't. Which is why we can make this prediction that there are two possible intermediates. One option, the carbon on the bottom of the alkene uses the electrons and bonds to hydrogen, leaving a positive charge at the top carbon. Option one, the electrons are used by the less substituted carbon, lost by the more substituted carbon. Option number two, the electrons are used by the more substituted and lost by the less substituted. You okay with this? Two carbons are sharing pi electrons. One of them gets to use the pi electrons, the other loses them. Those are the two options, but based on what we know about the product, which of those two options actually forms? The top has to be the intermediate that forms. Because now I have a magnet, positively charged magnet, that's going to attract my negatively charged magnet, my bromide. And when that bromide is attracted to that tertiary carbon on the top, only then am I able to form a tertiary alkyl halide. If my bromide was drawn into this positive charge on the bottom, I would have formed a secondary alkyl halide. I would have formed a structural isomer. And I don't form this. despite the fact that it's possible, but doesn't form. Tomorrow, actually probably more like next week, we're going to be diving into these reactions in a lot more depth, and we'll explain clearly why this structural isomer doesn't form, why this structural isomer is favored, and how to be able to make those predictions to be able to take a starting material and predict a product. Let's add arrows in the middle step to form the final product.
I'm sorry, you said that it is used by the more substituted carbon, which is on the top?
What is used?
The electrons when you break them down?
The electrons here can be taken by either carbon.
Right.
That's the possibility.
And the top one is, you said more substituted carbon?
If we form this top structure, it means the bottom carbon used the electrons.
Right.
And I don't, it is a little weird to, I don't know. I'm just trying to keep the color consistent. That orange hydrogen isn't necessarily anything special. It just was hidden before. But can you see how that orange hydrogen was there the whole time, but this new hydrogen is either added to the bottom carbon or the new hydrogen is added to the top carbon. In order for that hydrogen to go one place or the other, that carbon has to use the electrons to bond to it, which means the other carbon is going to lose the electrons. So in forming this on the top, we know that the bottom carbon must have used them. But how can we show that? We can't. I can't show it on my arrows. I just show it by drawing the intermediate.
Are you saying the bottom carbon took the hydrogen because the more substituted carbon has preference to take the bromine?
Not that the more substituted carbon has preference, just because we saw the product. So we know that there's regioselectivity. There's two ways this could have gone, and we're seeing that it selectively goes one way.
Okay. Based on the product?
Based on the product, yep. Rowan and then Andrew.
Also be based on, like, it's better to have the charge more substituted.
We'll talk about that tomorrow, I think. Yeah.
So, in like an actual lab environment, if you created this reaction, would you get that product, or could you get both products?
Yes, to an extent, you could get both. We would say there's a major product that is maybe 70% yield, and a minor product that is maybe 10% or less, and then perhaps unreacted materials, stuff like that. We can purify it though as well. We can, if it's a liquid, we can distill it and take just the product we want. If it's a solid, we can recrystallize it. If those options are too challenging, we can use column chromatography to try and separate them out. So if multiple products did form, because we're going to look at competitive pathways as well. If multiple products do form, we can usually separate them. Either way, we could analyze these and prove which one we got. Because this 1-bromo, 1-methyl cyclohexane has a very different NMR spectrum than 1-bromo, 2-methyl cyclohexane. Those have different NMR spectra. They'll have different fingerprint regions in the IR. So we could use our spectroscopy to prove which structural isomer is formed. All right, so we added arrows to the first step, and we saw that there were two possibilities. Based on what we know the product to be, based on what was given to us, we know that bottom possibility didn't form. So let's add arrows in this middle step with bromide and the top structure to form the final product. Bromide donates electrons to the carbon lacking electrons, to that positively charged carbon. Done. That's our two-step mechanism for this reaction. It included a total of 3 arrows. I want to point something out. There are people out there, and I don't know who they are. I'd like to invite them to my class. There are people out there that would suggest and even teach that you can use electron arrows to indicate which carbon is attacking, and they'll add arrows like this. They're trying to say the pi electrons get piled up onto this carbon, and from that carbon, they go on to attack the hydrogen. This, I think, is silly. It's not what's happening. Because the electrons are not piling up on a carbon and then moving from there. And if they were, this arrow doesn't say pile the electrons there first and then do it. This arrow is saying there are electrons here that are being used. And this arrow is saying there are electrons coming there. It would need to be steps. But it doesn't happen in 2 steps. It happens in 1 step. This is not a good way of using electron arrows. And I know some of you must have learned from people that learned this, because I saw it on the midterm. And I imagine it's not something that you guys invented, but it's not a great way of depicting how those electrons are moving. Now, let's say you do want to show that the electrons are coming from one carbon specifically. This arrow that I showed before, it really just leaves the pi bond in the middle. There's no way to indicate which carbon is using them, but based on the structure of the intermediate, it's obvious which one used them, or it can be determined which one used them. What if we took those pi electrons and we just swung around and through the carbon that's going to use them? Instead of coming out through the middle, we can just say these pi electrons are being used by this carbon. It's subtle. It says nothing different than what this says. It doesn't require this extra arrow like this one does, but it still gives you that indication of which carbon is using them. Does that make sense? This is perfectly correct. In fact, you would need to be able to interpret something like this. This is not ideal, but this is good. All right. Our 2-step and some implication of regioselectivity. Just because 2 possibilities exist doesn't mean that 2 possibilities will occur. Now, in this next one, I want to look at what happens when you have multiple steps, but I also want to show you guys that there are competitive pathways. I had this idea when I was in Florida last summer on vacation. We went to the beach, and there was this big puddle in the middle of the beach before we got to the shore. And when we left, that puddle was gone. And then I said, did the puddle evaporate, or did the water seep back into the sand? Maybe both. Why couldn't it be both? That water could have left that puddle by both evaporating into the air and draining down into the sand. That's a competitive pathway. 2 different routes to get rid of the puddle. A lot of that happens in organic chemistry as well. Same starting materials, very different processes leading to very different products. The end result is a reaction occurs. The puddle disappears. But what product is formed depends on how that happens. So we take this example where we have, what did I call that yesterday? DHM. Were you guys saying that in lab yesterday? Dihydrogen monoxide, and tert-butyl bromide. And we see that something will happen. All right, I want to point out this idea of magnets. This is not a very strong magnet. It's certainly not as strong as hydroxide when that oxygen holds a negative charge, because a more negative charge means a stronger negative magnet, if you will. So this is a weak magnet, and it turns out the partial positive on this carbon and the partial negative on this oxygen are just not strong enough to do any sort of reaction. Instead, what happens is the bromine gets kicked off. So the first change that we see is a carbon-bromine bond breaking, and it breaks towards the more electronegative atom. That leaves us with a negatively charged bromine and a positively charged carbon. So now we have this set of reactive intermediates. And it turns out that there are two things that can happen. What I'm going to do is actually redraw this so that I can show you those two different things. On top, we see that there's a pathway that takes us to an alkene, an elimination reaction, which means the other change that needs to happen is a CH bond breaks, and the electrons are taken by carbon to form a carbon-carbon double bond. Elimination, where a hydrogen is taken from carbon, that's a deprotonation step. Proton is being taken away from carbon. I need a base. This is acting as an acid. I need a base. What's a better base? Bromide or water? It's kind of strange, right? But water is a better base because HBr is a very strong acid. So we can show water acting as the base here. Water donates a lone pair of electrons to bond to hydrogen. That's going to form H3O+. But the CH bond is owned by carbon, and what does carbon want with a pair of electrons? Not much. So carbon will share that pair of electrons with the positively charged carbon adjacent to it. We've now shown two arrows, one that forms an OH bond, and one that breaks a CH bond, and the breaking of the CH bond immediately shows forming of the CC double bond. One arrow that's showing one change, another arrow that's actually showing two changes. Which means our last product, or our last byproduct of this step, Br minus. By the way, H3O+ and Br minus, that's what exists in solution if you have HBr in water. So if you had instead shown bromide as the base to form HBr plus a molecule of water, it would have just dissociated into H3O+ and Br minus. So it would have been effective, just less plausible. All right, on the bottom, we see that there's two more steps before we finally get to tert butyl alcohol and hydrobromic acid. Well, at some point, I'm going to need to form a CO bond, but I'll also need to break an OH bond. So one question is, do I break the OH bond first and then form the CO bond? Or do I form the CO bond first and then break the OH bond? These are the two things that need to change. Form a CO bond and break an OH bond. The question is, in what order should that happen?
Form the CO first.
Tell me why. Why do you think that?
Because if you don't do that, you can't put the OH anywhere.
Okay, so form the CO, which leads to already having an OH, then remove the H.
Form the CO and then break the OH.
Why can't I break the OH bond first and go from H2O to OH minus? To do that, bromide
Bromide.
has to attack water to take a hydrogen away from it, which would form HBr and hydroxide.
Is that hydrolysis?
That's not hydrolysis. Hydrolysis is just at large anytime you react with water. You remember solvolysis? It's a reaction with solvent. Hydrolysis is a reaction with water. What?
You could do that, right? But then you would just have an OH floating around.
Not just an OH, an OH minus. What do you know about these? Acid base. Do those exist together in the same solution? No, they don't. They react with each other. Even just before, we said it's more plausible that water acts as a base to form an alkene and form H3O+. That's more plausible than bromide taking the hydrogen because HBr is such a strong acid. How likely is it, if bromide can't take a hydrogen here, how likely is it that bromide takes a hydrogen from water? Extremely unlikely. So, plausibility tells us I can't break the OH bond first. I don't have a strong enough base to deprotonate water. Does that make sense? It's all acid-base chemistry, actually. I don't have a strong enough base to deprotonate water, so I can't break the OH bond first. I'll have to form the CO bond and then re-evaluate. All right, what I'm going to do is expand my two bonds from oxygen to the two hydrogens, because I want you to see what that looks like. If it helps, you can even do that in the step before and just show the molecule of water. But I want you to see all three of those bonds.
Is that like water and electron donor?
Water is the nucleophile. Yes, the electron pair donor, the Lewis base. I decided to form the CO bond. Now I need to break the OH bond. And I decided to do it in that order because there's no way that I could break the OH bond before. But now, breaking the OH bond actually makes a lot of sense. That's not water. That's a protonated alcohol. And I can deprotonate that alcohol. Bromide uses electrons. I'm using the negative charge because it implies an extra lone pair on bromide, but there is absolutely nothing wrong with drawing in those lone pairs and having that arrow start from the lone pair. Either way, start from the negative charge or start from the lone pair. Bromide acts as a base, breaks the OH bond. Why was it easier to break the OH bond this time than last time?
Because the O's got a positive, so it wants the electron.
Now oxygen is positively charged. You remember Cario? The more positive the charge, the more acidic it is. All else the same. And all else is the same. There's the same amount of induction, resonance, orbital. The atom is the same. The only thing that's changed is the charge. This oxygen is far more acidic than this oxygen. Saray, you had a question?
So I was going to ask, if then we had a strong base, like sodium hydroxide instead, then the breaking of the hydrogen bonds in water would be more plausible than the CO bond?
Sure, hydroxide can deprotonate water. But if you think about the reaction you're writing, if hydroxide deprotonates water, it forms hydroxide and water. That's a very useful thing because later in the semester, we will use alkoxides, not hydroxide, where hydrogen is connected, alkoxide, where an alkyl chain is connected. And we'll use a solvent that matches that alkoxide so that we don't ever get rid of the alkoxide that we want. But if I were to use water instead, then I get some mixture of hydroxide, alkoxide, and that's going to change my reaction. So yes, if there was something stronger, it would do something different, but we're going to talk about this reaction later in the semester too. And if there's something stronger, it's going to do something different. So everything changes when you make a small change, like putting in hydroxide instead.
So water can be an acid and a base, right?
It can.
So in this case, when it bonds, does it turn water into an acid? That's why it bonds to protein.
Well, here, water is a Lewis base,
Right.
the nucleophile. And here, there is no water, technically, because it's bonded to an organic structure. So it's an alkoxonium ion, protonated alcohol. But the idea that oxygen can be acidic or basic is still true. And so here it's acting as a Lewis base, but now it's acting as a Bronsted-Lowry acid.
Is that OH2 then? Is that what we call that? H2O?
Yeah. If you wanted to abbreviate that structure, it'd be OH2 plus connected. It's essentially water bonded to the molecule. Did you have your hand up?
I just wanted to clarify, our top arrow in the intermediate is signaling the bonding of hydrogen and bromine.
This one.
Yeah.
Yeah, bromide bonds to hydrogen.
So it wouldn't be right if you just drew the bond breaking, because then you would.
To be fair, some people don't include a conjugate base. So if you got rid of this entire part, you got rid of bromide,
Yeah.
and you just said the OH bond breaks to O, it would leave in its wake H+. And H+ is technically a conjugate acid. So in OChem 2, we actually do mechanisms where you can show it that way feasibly.
But for our purposes, we need to show the HBr forming and.
I think it makes the most sense for you guys to focus on what conjugate base is involved. What roles are the reagents playing?
So what's happening first? Is the bromine bonding to the hydrogen, which causes the hydrogen to want to break its bond, or is it bond breaking to the H and the O, and then the hydrogen drifts to the
Dominoes. Yeah, they're happening at once. If this is the OH bond, it's only because bromine is coming in that it's able to actually break that bond.
So because bromine's present.
Maybe not dominoes. Newton's cradle. Do you know Newton's cradle, where those balls, conservation of momentum? If bromide can come in at the right angle and with enough energy and bond to hydrogen, then the electrons get kicked out back to oxygen, who was already pulling on the electrons anyways.
Okay, that makes sense.
All right. Same exact intermediates, different things that they can do. That's something that we'll also approach this semester. How do you predict multiple different products? One of them is a substitution pathway. One of them is an elimination pathway. How do you predict multiple different products? Can you change the conditions of the reaction to promote the formation of one over the other? That's something that we'll come back to. The last thing on this worksheet is actually not something we'll do, thank God. This is total synthesis, is a term that's used mainly when we are making molecules that nature is really good at making. So cholesterol, something that I believe your body makes. I don't think you have to ingest cholesterol. Your body is able to synthesize cholesterol. If you as a person wanted to synthesize cholesterol, you'd start with this structure. I don't know what it did to me, but my oxygen, that's supposed to be a methoxy ether. The oxygen is written really weird. You can start with this structure and then transform that structure into the steroid base template, this ABCD ring, 6-6-6-5 membered ring. And you can do it in 34 steps. The first ever total synthesis of cholesterol was done in 34 steps. Today, that's considered a terrible synthesis, terribly inefficient. That's too many steps. But it was an impressive feat at the time. In fact, it's still impressive if you can do it. The synthesis on the right is the first reported synthesis of penicillin, done in 7 steps, a lot more efficient and still fairly efficient for what we're able to do today. These require multiple reactions, 34 reactions or 7 reactions. Later in the semester, we're going to do multi-step synthesis. We're going to go through that process of taking an alkene, making an alcohol, going from the alcohol to an alkyl halide, and from the alkyl halide back to an alkene. Being able to do not just one reaction to synthesize a new functional group, but synthesizing a functional group that can then be used to synthesize a functional group that can then be used in another synthesis. Multi-step synthesis. You won't have to do this, but I wanted to give you a cool example of what multi-step synthesis is and how chemists are using synthesis. All right, so that's it for that worksheet. Now, before we do the next worksheet, I'm going to have you guys get into an activity. So we're going to break into 3 groups, and you're going to work with these sets of Post-it notes. The starting materials are shown on the left, the products are shown on the right, and possible intermediates, well, maybe not even possible, structures are given to you. The actual intermediates are present, and you will need to rule out any structures that are not plausibly part of the mechanism. These are not, I want to be clear, these are reactions that you will need to know by the end of the semester, but I do not expect you to have any mastery of them right now. This activity is to have you engage in that thought process of what is plausible, what is feasible, what is not feasible. Like when we said here, 2 possibilities exist. I could deprotonate the OH first and then form the CO bond, or I could form the CO bond and then deprotonate OH. We had to talk about the feasibility of that. That's what you'll have to navigate through here as well. So could I have you guys stand up in a line like you did again? Maybe we do a semicircle through the room, and I'm going to pair you up. I want closest to January 1st birthday here, and closest to December 31st birthday here. So you guys, without talking, are going to try and organize yourselves by birthday, January 1st to December 1st. You can say, I'm pretty sure that I'm, but you can't say your birthday or your month.
Can you say how old you are?
I don't know how that's going to help.
What if I say it in months?
No, you just have to work with everyone else to try and place yourself where you think you are. Yep. January on this side,
Pretty confident.
December 31st on this side.
We're in a circle.
You're going to, yeah, kind of, because I remember this was hard to do the last time, so you're just going to kind of bow around. All right, well, you guys organized. So now if you want to say your birthdays and see how much we have to move. Ooh.
August 21st.
Oh, Evelyn, I think you might be in the wrong spot.
June 21st, June 20th.
Ooh, that was very close.
Yeah, October 4th.
October 17th.
October 25th.
December 4th.
Okay, so Delaney is ahead of.
Pretty good.
Okay. Wow. Isn't that impressive?
Mm-hmm.
Without communicating, we had 3 errors.
And by a day or so, we were close.
Yeah, very close. How many birthdays were just one day apart? 20th and 21st, 7th and 8th? That's wild. All right. So Andrew and Quinn. Oh, wait, I've got 3. How many of you are there? 3, 6, 9, 12. Oh, so we're going to do groups of 4. All right, so Quinn and Elvira, Chloe and Andrew, you guys will work over here on that mechanism. Patrick and Liana, Gavin and Delaney, you guys will work over here on this mechanism. And then Rowan, Saray, Evelyn, and Berkeley on the back mechanism. Okay, I'm not telling you how many steps they are. I'm not telling you how many intermediates you should find. That will just be for you guys to discuss. Use your vocabulary. Try to talk about what's feasible and what's not feasible. We've got 5 minutes to start, and we'll see if we need more time after that.
So we can talk.
Yes.
We're trying to figure out which one of these are right.
Oh, of all four?
Trying to organize the mechanism.
No, because there's an H breaking off this and attaching to the OTS.
So it is a.
So this needs to break, that needs to break, this needs to attach.
Because this bond would go.
Oops, sorry.
I think it is a substitution.
Yeah. It is.
I was thinking like instead of just swapping places or shit.
Yeah.
No,
There's
yeah,
more to it.
breaking it.
No.
Yeah, exactly, okay.
Or maybe not. Or maybe.
Oh, maybe.
Right.
So I think.
Should I tape that one down more? The one that fell?
And then this one is wrong. Because bromine would be negative.
Yeah.
Oh, man.
And that can't be negative.
If you have to set it on a desk, it's not the end of the world.
Yeah, the O's definitely gonna take the.
Is this one for sure now?
I think so. Yeah, because I think it would be that instead. This one's for sale. I mean, this makes no sense. Yeah. Yeah. It wouldn't have a negative. And I don't think hydrogen. Yeah, that's just an electron.
You guys think you got it?
I hope so, sure. But maybe, yeah.
Can I hear your rationale?
Well, first, is it right?
It came from the H.
It is.
Hell
Okay,
yeah.
cool.
Okay. Well,
Now we know we're thinking about it correctly.
yeah. I was gonna try to explain, but I'm not.
So your explanation could include two things. Your explanation could include why you ruled those ones out or why you ruled those ones in.
Well, first, we talked about what needed to break and what needed to bond, what kind of a reaction it was. And then we said, well, we won't have a negative charge on this carbon, that doesn't make sense, and this doesn't make any sense.
Okay.
So then we were between these two,
And why does the top one not make any sense?
because why would we have a positively charged, like, what would be the purpose of having these?
I see a positively charged oxygen up there.
Yeah, I guess.
Yeah, but they don't
but
need
that
to
one's
both
not
bond to
neutral.
alkane.
But why are they
There's only a
both on- why
positive,
would they-
there's no negative, so it's not a neutral.
In fact, there's a typo on that. There should be a negative charge on the carbon.
Right, yeah, and because there isn't, like, we know that.
Sure, sure.
What was that? You didn't mean to not put that?
Let's say I fixed it. Let's say I did put a negative charge on there.
Right here.
Yeah.
I still, in my head, it just doesn't make sense, because then what? Like, these are both here, and then they just break.
And then what if one of them leaves as minus OTS?
Well, because it doesn't make sense for a hydrogen to break off on its own like that.
Well, it doesn't have to, right? You could go from that top structure to that second to last structure that you have.
I guess, so is that an option?
Depends, but if you have that negative charge on that carbon, there's a reason you should still rule it out.
Yeah, it could be either one. Yeah, I know, I was just like, it just doesn't make sense. Why would the carbon be negative?
Because of
It
that.
has an extra electron. It has 5. Oh, so you're saying the hydrogen, well, it doesn't make sense for a carbon to have 5 bonds.
Nailed it. Nailed it.
That's why, because we,
Can't.
right, and because.
Like it can, but that's just not gonna happen.
Correct.
Carbon has-
Correct. Texas carbon. Okay, you guys think you found it?
Yeah.
Nice. So you ruled out 3 of the structures.
Yes.
Why'd you rule out this one?
The hydrogen is negative,
That's crazy.
yeah,
Why'd you rule out this one?
the bromine is positive.
Yeah. What about this one?
The carbon would have 5 bonds, because it's negative. negatives?
It actually would, it had one hydrogen, so it still has one hydrogen.
Yeah.
So the negative charge actually indicates a lone pair,
Okay.
which is possible.
Okay.
That carbon can have 3 bonds in a lone pair. But why would it, right?
Yeah.
If there's a version where bromine can have the negative charge, then it should do that. Great work. You guys can leave. I'll actually take these. You guys can leave that if you want to. Thank you. How do you guys feel? Which ones are you doing? Both? Top?
Saying
Yeah, we think
both.
there's two possibilities.
It's possible, but it doesn't form. It's one of the top one.
We think the bottom's preferential.
Yes.
So you think in the bottom route, these things all happened at once. The hydrogen was donated to the oxygen of the alcohol, and the carbon-oxygen bond broke at the same time.
You're saying that OH got cleaved. Because we thought it was elimination reaction.
Sure, you're saying the CO bond broke, and at the same time, the oxygen bonded to a hydrogen from the acid.
Yeah. Can that not happen at the same time?
Well, it can, but if there's a way to do it in multiple steps, maybe that's more feasible.
Oh, so you're saying
Right.
do that before.
And then how feasible is it to protonate sulfuric acid?
That makes sense.
Is it easy to give a proton to the strongest acid? Is it easy to protonate a strong acid? No, it's really not. So I think that top structure,
Because we protonated it, so that's got to be no.
yep, top structure feels very implausible, almost as implausible as this, where, again, they're both protonated forms of sulfuric acid.
Okay, so we.
So this is like, it's the steps.
Okay,
It's
so
not
deprotonating the
one or
acid
the
is
other.
what makes the most sense.
Mm-hmm.
Because that's H2SO4, which is a hydrosulfuric acid.
Yep.
It's extremely strong, so we want to deprotonate.
Sulfuric,
immediately.
not hydrosulfuric.
Sulfuric, sorry.
Yep.
Sulfuric acid. What's the difference?
Hydrosulfuric acid is H2S.
Oh, okay.
Like hydrobromic acid is different than bromic acid.
Right. Okay. So we want to deprotonate, which would cause it to attract to the OH.
Good,
And then from there it cleaves off as H2O.
good. So you have an acid, you should be thinking about what will be the base.
Okay.
The only thing here that can be the base is the OH. If that acts as the base, this is the structure we form. Now that we formed that, we can see water leaving the molecule and then an elimination happening.
Okay, so we can add before we eliminate.
There's a lot
Yep,
of different ways
yep.
to look at it.
There are a lot of ways. Great work, you guys. What did that process feel like? Blind leading the blind? All right, so this group over here, you guys had a structure called, well, I actually am not very good at naming this, but this is a group we'll talk about later in the semester. It's a tosylate on cyclopentane. And the final product that you were given showed what type of reaction? Addition, elimination, substitution? Substitution. Overall, it's substitution. And some of the structures that you threw out were based on the fact that they didn't seem plausible. So you guys threw out this structure. And tell me why you threw this structure out. That's a 5-bonded carbon. It's hard to see that it's a 5-bonded carbon because that hydrogen is assumed. But there's a hydrogen at that carbon. And in order to get a negative charge on a carbon with 4 bonds, there must be a 5th. That would be 4 minus 5 is -1. So they threw out this structure because it has a 5-bonded carbon. Doesn't make any sense. they also threw out this structure because it doesn't make sense to break the charge apart, giving carbon more negative than oxygen and giving oxygen more positive than carbon. That just wasn't a feasible pathway. So the pathway that they chose was to show this OTS group leaving as OTS minus, leaving a positive charge on the carbon, before the other oxygen adds on and then gets deprotonated. So they did substitution, which required breaking a CO bond, forming a CO bond, and breaking an OH bond. And they did it in the sequence of break the first CO bond and leave carbon with a positive charge. Form the second CO bond and then deprotonate it, which followed a lot of what we have already seen. The group that was in the back had this reaction. And they threw out structures that included, some of these I forgot charges, which didn't make it easier. They threw out this structure because why in the world would hydrogen take on a negative charge? Good point. If you see something like that, maybe that's not something you should be seeing. They threw out this structure for some of the same reason that you guys threw out this one on the right. Why is bromine taking a positive charge so that carbon can take a negative? That doesn't seem right. It doesn't seem plausible. And then the other version that they threw out was this version. Now, it's not that it seems bad that that the carbon is negative and the hydrogen is positive, because that's better than a negative hydrogen and a positive carbon. But when there is a bromine in the molecule or in the reaction, why would that negative charge end up on a carbon? That's challenging. And the one structure that they decided to keep, that they believed was part of their intermediate, was this, or part of their reaction. Great. Which actually looked a lot like that regioselective example that we did. Of the alkene, H adds Markovnikov and Br adds to the more substituted carbon. Okay, and then the last reaction was an elimination reaction where they took rubbing alcohol and made propene plus H2O and H2SO4 using H2SO4 in the starting material. Some of the structures that they threw out. They threw out an option where sulfuric acid gets protonated by the alcohol. That's a crazy thing to show. Sulfuric acid is the strongest acid that we'll work with in lab and in lecture. It's not the strongest acid, period, but it is very strong. So to protonate it, very hard to do. They also threw out another version where water was kicked off, but they still had this protonated sulfuric acid. I think the problem about this one is the number of hydrogens has actually changed from the starting material. There's too many hydrogens in that structure. There's too many. The structures they decided to keep was when that strong acid protonates the alcohol. Now that makes more sense. Sulfuric acid looks to get rid of an H+. Who can take it? The lone pair of oxygen can take it. Then they showed that water can leave. And in this last step, they're showing an elimination where a hydrogen is taken from carbon and given back to our conjugate base to reform the acid, in the process forming an alkene. So you guys did substitution, addition, and elimination, each with different number of steps. No, I guess these are 3, 2, and 3. But a lot of it came down to, can I rule out what's plausible and what's not plausible? And I want you guys to think about that this semester as we do reactions and as you draw arrows and as you predict intermediates. Does that feel plausible that the charge ends up where it does, that the charges are separated the way they are? Did you consider acid-base chemistry? If you see an acid, what do you think that acid is going to do? Where is the base if you're seeing an acid? Those are questions I want you guys to think about as we do more with mechanisms this semester. Okay, now more practice. Gavin? Maybe. I will check.
With this, are we able to draw arrows like we did last time, or is this the most simple way to draw this type of reaction?
Oh, no, no, no. Can you hand this back to you and Quinn? Oh, and one more behind you to Rowan. This is not truly a mechanism. Sorry. I think I'll put this on Canvas right now. I don't think that I left it up. In terms of a mechanism, this is not an electron arrow pushing mechanism yet, because all we're showing are starting material, products, and intermediates. But this would be a good template that we could come into and add electron arrows to. We could show the electron arrows. Gavin, since you asked that, what electron arrows would you expect to see in the first step on the left? Mm-hmm.
Well, I asked you.
Yeah, you didn't know if we could, and I'm telling you we can, so now you tell me what we should.
Like in the very first step, or like the second?
In the very first step, from the OTS bonded to cyclopentane down to the positively charged carbon. Mm-hmm. Okay. What change would you expect to see? Or what arrow would you need to add? Okay, Elvira, it's on Canvas. Practice mechanisms.
That carbon bond to the OTS?
From the CO to the O.
Yes.
Good. Because that bond needs to break, and those electrons are owned by oxygen. Somebody else want to share what electrons we need, what arrows we need to add in the second step?
The O to the positive carbon.
More than just from the O, it's the lone pair on the O. This is what I refer to as relevant lone pairs. How many lone pairs on that oxygen? 2 lone pairs. One of them is relevant in forming the bond. The other one is irrelevant. So I need to see relevant lone pairs, because if your arrow starts at the O, that's not an electron source, that's a nucleus. O represents the nucleus. The electrons have to be drawn in for the electron arrow. Does that make sense? But you can show both lone pairs. It's just that one of them is relevant. What about in the next step, in the last step? What electron arrows need to be shown?
So we won't be able to show like the arrow coming from the bottom pair, right? The electrons just.
You could. But you shouldn't show it from both, because it's just one of the pairs.
Be a lone pair from the TSO taking the oxygen.
Taking the hydrogen. Now we could draw in, there's 3 lone pairs on that negatively charged O. We could draw in the lone pairs, or we could start from the negative charge, because the negative charge on oxygen implies a lone pair. But that shows me forming a bond to H. Oh, it should go the other way, from H to oxygen? Parking spot moves to car. Right. From the negative charge to the hydrogen, but
You'd have to show the bond of the hydrogen going to the oxygen.
exactly, I can't form a second bond to H unless I also break the bond that H is already in. And that bond is not shown. So I need to draw it in because I can't assume that bond breaking. Have to draw it in. I can't even just draw an arrow from where it would be. That doesn't show the electrons. And since it's the electrons moving, I have to show the electrons. Okay. What about electron arrows to add to this one? In the first step?
You show the double bond breaking to the hydrogen,
Double bond to hydrogen.
and then you have to show the bond between hydrogen and bromine.
Good. So I did not set myself up for success. Now I have to restart and draw that HBr bond. And then I can successfully break the HBr bond. What about in the second step?
Electrons from the bromonated going to the oxide.
Good. Do you guys notice again how my electron arrow doesn't show which carbon is using it because it doesn't need to. But if you want to show which carbon the electrons are coming from, then you can just get a little fancy with how you draw your arrow. There's nothing wrong with it. What about in my last one? Oh, you know what? This one's a bit of a pain because I have to draw sulfuric acid. I have to draw sulfuric acid so I can show the OH bond breaking. What arrows do I need in the first step?
The deprotonation of sulfuric acid.
Lone pair attacks hydrogen, OH bond breaks. What about in the second step? What arrows should I show?
Well, are we cleaving H2Os? Do you have to draw a step of cleavage between the bond breaking?
Bond breaking.
So then the OH bond goes up, basically, something else with OH.
CO.
CO
CO
bond.
goes to O.
Yes.
CO bond points at oxygen. And in that last step,
We have that CH3 and the carbon hydrogen bonds going to SO.
good. I have to draw in one of the hydrogens that was assumed because one of the hydrogens has to be removed. And sulfuric acid's conjugate base bonds to it, which allows the CH electrons to be moved over to become carbon-carbon pi bonding electrons. How much acid-base chemistry did we see here? This is acid-base. This is acid-base. This is acid-base. This is acid-base. Anywhere there's just an exchange of protons, we're seeing acid-base chemistry. Then we have nucleophilic and electrophilic chemistry. Lewis acid-base chemistry. 1, 2, 3. I don't even know if we'd count that, to be honest, as Lewis acid-base chemistry. Half of our mechanisms are just regular acid-base chemistry, proton transfers. Another reason why we introduced acid-base chemistry so early, so that we can talk about why things take protons and why things give them away. All right, on this next worksheet, and we've got 25 minutes that we can spend working on it. Our goal is to spot the difference, what change happens at each step, and draw arrows for that. If we were to write this out as like a spot the difference thing, I'll do it for this guy. I need to see, over the course of the first step, I need to see HBr break and the carbon-carbon bond break, and I need to form a carbon-hydrogen bond. Those are all of the changes happening in the first step. In the second step, I need to break nothing, but I need to form CBr. On the midterm, a lot of you predicted the product based on the arrows given, but you didn't base it off of the arrows given. A lot of you drew products that had nothing to do with the arrows that were shown on the starting material, which means that you were guessing at what change was happening rather than interpreting the arrows. This is another way of seeing this, which is the arrows say break the carbon-carbon bond, form a carbon-hydrogen bond, break a hydrogen-bromine bond, which is also the change that we see. The arrows say form a carbon-bromine bond. This is what we need to practice. We just need to practice interpreting electron arrows forward and backwards. When you read arrows, can you interpret them? When you need to add arrows, can you interpret them?
This didn't start making sense until today.
Good.
So I didn't dig it on it on the midterm.
I get it. But that's why it's on the midterm, so that it's not an entire shock when you see you have to solve mechanisms like this on the final. You'll have to solve 2 mechanisms on the final. We'll talk more about that when we get closer. All right. Should we go through one of these together? Okay. Do you want to pick one from the front page? The back page says radicals and resonance. The front page is add the arrows. The second one? Do you mean the middle or the top right? Okay, that's a good one. This is a one-step reaction. Did I draw that right? Okay. Okay, can we spot all of the bonds that need to break? It might help if we map things, wouldn't it? So that we can keep track of what bonds are forming and what bonds are breaking. And we're going to look at this reaction later in the semester, so you don't need to understand right now how I'm deciding to map this. But I'm going to map this as 6 carbons that are going through a change. So now I can say things like form a carbon 4 to carbon 5 bond. I need to form a bond between 4 and 5. And that's what mapping allows me to do. Is figure out what bonds need to form and what bonds need to break. I also need to form a carbon 1 to carbon 6 bond. I also need to form one more thing. Can you see it? What other change is happening forming a bond? Got that?
Oh, sorry.
That was good. Between 2 and 3. There was no double bond between 2 and 3. Now I need to form a double bond. What bonds do I need to break? Well, I need to break the carbon 1 to carbon 2 double bond, the carbon 3 to carbon 4 double bond. What else? I need to break the carbon 5 to carbon 6 double bond. Here's the deal. For every bond breaking, I need to have an electron arrow that starts at that bond. A bond can't break unless those electrons go somewhere. So for all of these bonds, especially since this is one step, all of these bonds will have an electron arrow coming from them. And the question is, where should they go? And there's a lot of there's two right answers here. The electrons between 1 and 2, well, those electrons are either used by carbon 1 or they're used by carbon 2. Those are the two possibilities. If those electrons are used by carbon 1, what will carbon 1 do with them? Bond to 6. If the electrons are used by carbon 2, what will carbon 2 do with them? Make a double bond between 2 and 3. Either direction you go is correct. I'm going to decide to show the pi electrons between 1 and 2 moving to form the pi bond between 2 and 3. I have completed 2 of my 6 changes. Now that I've decided that's how I want to start, the rest of my options become clear. I'm no longer going to have to make the same decisions back and forth. 3 is gaining electrons from 2. 3 needs to lose electrons now. Good. Its pi bond is breaking. So who gets to use the electrons? 4. Because carbon 3 needs to lose them. And what is 4 going to do with them? 4 is going to bond to 5. 4 to 5 bonds. 3 to 4 breaks. Again, my 5 to 6 bond needs to break. 6 needs to use them because 5 needs to lose them. And 6 is going to bond to 1. Cycloaddition. 2 things coming together and making a ring. Great. Okay, do you want to take 10 minutes and solve the other 1-step, the 2-step, and the 3-step mechanisms? Feel free to collaborate. Definitely when you're done, collaborate and look through each other's solutions. I'm here to answer questions, and then we'll flip to the back side.
What?
Sorry. Bless you. Yeah, I just like doing that sometimes.
Okay.
It's Arabic.
Oh, okay.
I know some of those shapes. Yes.
Do we have to draw in VR? Because VR is missing on the first one.
Oh, sorry. On the first one? Oh, it's a byproduct, so you can show it if you want to.
Okay.
Yes, I can see how that would make it more challenging to not know. BR minus.
Okay.
Oh, you guys swapped.
Yeah.
This is going to form one bond between chlorine and one of the carbons. And this is going to form chloride. But how are you going to form the other bond to the other carbon?
That's exactly what I was wondering.
You want a tip?
Yeah.
Look at all of your lone pairs and watch how your lone pairs change. Yes.
For this back page, are you still drawing
We're
arrows?
yes,
Back page?
yes, but we're going to use different arrows.
Okay.
So you're done with the front page?
Did all of them? I
Wow.
think.
Wow. Oh, no lone pair. You need to show your lone pair.
Okay, so
Oh.
draw them in.
Yeah, yeah.
Okay.
So like this one, it starts from a negative charge because that implies a lone pair.
Okay.
These start from pi bonds.
Yeah.
But if it starts from a lone pair
Okay.
and we
Drop it.
aren't showing it, we have to
Okay.
show it. Now, in addition to that,
Yes.
this is going to form a bond between carbon and this chlorine. If you showed the lone pair here, I would say this forms a bond between the other chlorine and the other carbon, but that doesn't break the chlorine-chlorine bond.
Oh, because they're.
In other words,
Yeah.
this looks like carbon 1 bonds to chlorine 1, and carbon 2 bonds to chlorine 2.
So yeah, we need to break this.
Okay. This will form your chloride.
Yeah.
This will form one bond between one carbon and one chlorine. But what about the other bond between the other carbon with that same chlorine?
Let's see, chlorine has, so you draw this and do that?
Yes,
Okay.
exactly. And if you pay attention to what's happening in the lone pairs here, that's exactly what happens. 3 lone pairs, 2 lone pairs. One of its lone pairs must have been used.
Okay.
In forming
why
a bond.
it's positive.
Yes. And then these are perfect. Great job. Oh, what's up?
Oh, sorry. So then, like, going with this, because with this, like, this has one hydrogen, so then, like, breaking the double bond, it doesn't necessarily go into the carbons, though. It goes through one of the carbons and then it attracts one of the chlorines, right? So then, it's okay doing it.
Sure.
Like this
Great.
way, 'cause then that, like,
Shows the formation between carbon and chlorine.
that, and this bond goes in, there's that goes in seal.
That shows the formation of chloride.
Yes.
Great. But this says one carbon bonds to chlorine. How do we get the other carbon to also bond to chlorine?
Because that also has the H. That's a great question.
Yeah, Saray wrote it down as form 2 carbon-chlorine bonds, and so far we're only showing 1. Do
One.
you want a tip?
Yeah, sure.
Use your lone pairs. Draw out all the lone pairs and see how the lone pairs change. Did that help you solve it? Really?
Is
Mm-hmm.
great.
That's exactly it. This is great.
Yeah.
Perfect. That's it. Doing great.
So does another one of the lone pairs go to the other carbon?
Mm.
So then it comes back?
Yep.
That's gonna break.
Look at that, like that?
Exactly like that.
Oh, wow.
Where's this arrow starting
So
from?
alkene,
This arrow?
first off, this bond
Yeah.
with
Starting
makes
from-
chlorine minus,
Oh,
and this
from the
alkene
negative.
Okay,
bonds to this
good.
chlorine, which makes the first
And where's it
bond.
going?
And then
To
that
the
second
bond.
electron gets like sucked down and attracted to
So
that carbon.
the negative charge is
So then now you have 2 bonds.
putting more electrons in a bonding region?
It's
So this
creating
first carbon bond from the alkene, second
To
carbon
what
bond
atom?
from the lone pair with chlorine.
to the
But why is it
carbon.
Okay, so we should show it going to the carbon
Because it's a weird double.
because
I forgot what the structure's called. What's the
No.
structure called again?
chloronium ring.
It's
Chlorine.
the, oh, to the
I don't know why you would
carbon.
know that though.
Well, like whenever there's like the two, like coming off of a
s-
carbon chain, like 2 bonded to something.
Epoxide?
Epoxide.
Yeah, but epoxide is when it's oxygen.
Okay. But that's how we see
It's very similar to it, yeah.
Okay, so even if it's creating a shared bond, it goes to the atom that it's creating the bond with.
Yeah,
that
yeah.
makes sense. Okay.
Um,
Because it's not just going to like this
Yeah.
space in between, thing.
exactly,
It's going to it to create the bond,
exactly. Great.
Great. Great.
We're gonna
Oh, great.
we're gonna get to that. Why don't you talk with some others though and see if you all agree. I think Andrew would be a good one to talk to, Evelyn. He's at the same spot as you.
I'm scared to wreck the arrows because
I know you are, I know. This forms your chloride, so that's great. Where is this arrow starting from?
yeah,
What is it
I
starting from?
figured that it was the electronegative, but it should be from the double bond to the chlorine.
but what is it starting from? What electrons is it using?
The lone pair.
The lone pair. Good.
Should it be going from the lone pair to that?
Well,
'Cause
that-
I thought that the double bond is always the nucleophile.
Why can't both be true? You need to form 2 carbon-chlorine bonds between the same
One
chlorine.
lone pair should attack and then one. How could this be? Oh, because that has to break to attach there. Oh, okay.
Adam.
Just towards the yeah, because it can't just lob its electron at the bromine. Well, the positive electron, the positive is on the oxygen, so we have the same thing, right?
Where's this arrow
But not-
starting?
At my hydrogen, I need to draw it the other way.
Oh, okay. Because otherwise you were saying a nucleus is moving, but these are electron
Yeah, as
arrows.
long as the arrows are the right way, then these are the same.
Yep.
I was just wondering why both of your arrows were going out. Yeah, no, this one was the wrong way. Is this wrong?
Nope.
Is this wrong?
Nope.
Oh, wow. Go me.
Nailed it. Great work. This is exactly right. Yep. Perfect. All right. You guys almost ready?
Professor?
Yes.
Because then, like, whatchamacallit?
Why does this happen? Why doesn't it just go here immediately?
Electronics and sterics.
Is this because?
So it's this positively charged, yeah.
Oh, he was also asking how come the chlorine isn't bonded as chlorine.
Too many.
Like,
But is it because of electronegativity rules?
I agree. We would,
it'll look like it's just another chlorine.
but this chlorine already has a full octet. It's got 2 bonds and 2 lone pairs.
But it's positive.
And it doesn't want to accept more electrons, it just wants its electrons back. So, despite having a positive charge, it is the carbon that is electrophilic. The carbon has a partial positive
Is that because of the electronegativity differences in carbon?
because chlorine's more electronegative. Or think about this, Rowan. In a deprotonation, if I have something like hydronium, and then I have a base, keep it simple, like hydroxide. Does hydroxide bond with the oxygen and form an OO bond?
No, I guess the arrow is just kind of confused because it looks like that's what
It looks like that those 2 magnets should get pulled together. But what's strange is that the partial positives play a bigger role. And instead of attacking the positive charge, it attacks the partial positive, which still allows the electrons to go back and neutralize.
So the arrow shouldn't even be drawn to the positive then, it should just go straight.
Depends on the positive. If the positive's on a carbon, yeah, the arrow usually goes to it. But if the positive's on a chlorine or an oxygen,
If that's an octet, though, why is it positively charged?
that's an octet too, and it's positively charged. Charges come from valence electrons minus shared and non-shared electrons.
Formal charge?
Formal charge.
Oh, that's formal charge.
Yeah, that's all formal charge.
Valence.
It doesn't say that it's missing an octet. No, formal charge does not imply anything about octets.
Couple questions.
Yes.
First, am I thinking about
I
this the
thought
right
it
way?
was valence here this whole time.
That this breaks, it's gonna add an electron to this carbon, which makes it negative, which is gonna make this positively charged chlorine once this breaks attracted to it.
So the electrons are not first taking a pit stop at this carbon and
That's what
then
you were talking about before.
picking up. Right.
Okay.
They're just, yeah, maybe you want to say they're being used by that carbon, but there won't be a first then.
It's more situation.
Yep.
Okay. Okay. So it's
Now,
gonna-
if this bond breaks, it forms the chloride.
which would be this one.
Yep. And this arrow is showing one of the carbons bonding to chlorine, but not the other.
And so that's, okay, how do we get this second bond? Because wouldn't this now be 1, 2, 3, 4, 5 with the hydrogen? How does this other bond get there?
Well, what is happening with all of your lone pairs?
I know, right?
You've got 6 lone pairs here. Where are all of those lone pairs here?
Then you have 1, 2, 3, 4, 5.
Do you want to just draw in the lone pairs that are needed? That's what you're trying to do.
Because there's not, okay, this has a hydrogen here.
On the bottom one?
And then this would go, this is my positive.
So I did this first, and then yeah, that just but this is because it's on dipoles.
Wait, wouldn't these be, wouldn't these
Form two separate
form this bond? Like, wouldn't it essentially be like that?
But you're not showing that. You're saying these electrons are forming that bond.
That just like swings down.
Oh, so then it would be,
Bonds to that carbon bond.
Now, if we do the formal charge calculation, are we going to get positive 1? Formal charge for chlorine.
You could say, well, if chlorine's positive, when chlorine on chlorine, but it doesn't. Because more carbon on carbon for the dipole. Because electronegativity. This would make it non-polar. And then that says. Yeah, you're right. I'd rather steal more electrons. And bond something more preferential for it. Yeah, so it would have to be two.
So Liana,
so no, it would be neutral.
if I need a +1 on that chlorine, and there's 7 valence electrons minus dots plus lines. How many lines?
Or, oh, 2 because the second.
Means how many dots are needed?
It just does that. It's just like that.
Yeah, 4 dots, 2 lone pairs. So the chlorine starts with 3, and then it ends with 2, which means chlorine is using a lone pair to make a bond. So the pi bond attacks chlorine, and chlorine attacks back. That gives you your 2 bonds formed. All right, I want to take a second on the back side to talk to you guys about radicals. And I think the start of tomorrow's class might include a little bit more on this. I think at the start of tomorrow, I'll put up the answers to these problems so that you guys, to the whole thing, so that you guys can copy them down at the start of class tomorrow. Because I also have resonance I want to show you guys. Anyways. So what do we know about radicals? We know about radical cations form in molecular or mass spectrometry. What else do we know about radicals? Unpaired electrons, unstable. How many radicals in this starting material? 0, because we can't assume radicals. They're not lone pairs. We can assume lone pairs, but we can't assume radicals. Radicals have to form by initiation. That means no radicals form 2 radicals. Now, to show radicals, starting from no radicals, I have to take a pair of electrons and separate them. How many electrons are represented by this arrow? 2. Because that's what we've been doing this entire time, and we've been showing 2 electrons. So how do I represent 1 electron? Yep, low fishhook, half arrow to indicate 1 electron. So in the first step, where I form 2 bromine radicals, I need to break the bromine-bromine single bond, but not by heterolytic cleavage. I need to break it by homolytic cleavage. 1 electron goes to each bromine. Those are not full-headed arrows. Those are fishhooks. The next step that we see is called propagation. What do you guys know about propagation?
Like a small thing off something and then it grows into something bigger.
That's what I think of. I propagate my plants. I take these cuttings from them, and now I have 10 plants. Not in radicals. Propagation is not increasing the number of radicals. Propagation is 1 radical becomes a different radical. The radical propagates to a different species. So initiation, 2 radicals form from nothing. Propagation is 1 radical becomes a different radical. In this step, we can see that one of the bromine radicals bonds to a hydrogen and becomes HBr. And the carbon that lost the hydrogen becomes a radical. So this CH bond needs to break to the carbon homolytically, fishhook arrow, and then a bond forms between the other electron and the bromine. That's a weird way of showing a bond. Our previous arrows have just said electron pair goes to that atom, but now I'm having two radicals interact, so they have to meet in the middle to form their bond. That's how we're going to show it. And then in the last step, two radicals become no radical. What would you name that? De-radicalization. How about keeping in mind that we call the first step initiation, termination. When you take two radicals and end with no radical, once again, my two radical arrows meet in the middle because my two radicals are coming together to form a covalent bond. There's your first radical mechanism. The electrons are different. The arrows are different. When we come in tomorrow, I'll put up the answers for the other problems. Feel free to take a stab at the last reaction you see on the bottom as well. And then we're going to move into alkenes. And next week, we're doing alkene addition reactions. And we're going to be learning about reagents, products, stereochemistry, regiochemistry, mechanisms. We're going to have a fun week. Have a good night. Good day. See you tomorrow.
So this bottom one doesn't have the radicals, we have to draw them in.
There are no radicals on this one.
There's just that.
Yep. That one's resonance.
Yeah, we can.
I just pulled it on my iPad, I don't know if you can
Thank you.
make use of that.
I appreciate it.